Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic problems on path loss and field strength. This topic is related to the course antennas, waves and propagation. So today's topic is problems on path loss and field strength. So let us start our session. A communication link is to be established between two stations which are 1500 kilometers apart. The maximum usable frequency chosen is 37.95 MHz for a thin ionosphere at a height of 250 kilometers. Calculate the critical frequency in megahertz if the Earth is assumed to be flat here. So here there are two stations which are separated by a distance of 1500 kilometers. So between the transmitting antenna and the receiving antenna, the distance is given as 1500 as in the problem given. The maximum usable frequency is chosen to be 37.95 MHz. So the maximum usable frequency, let us denote by the symbol FMUF is equal to 37.95 MHz for a thin ionosphere at a height of 250 kilometers. To calculate the critical frequency in megahertz if the Earth is assumed to be flat. And also the height from the surface to the ionospheric region, it is given as height h is equal to, it is 250 kilometers. So this is the given data, and we need to calculate the critical frequency assuming the Earth as flat. Here the condition is Earth as flat. So this is the basic condition which we are going to assume in our problem here. Now let us see what is actually the MUF, the maximum usable frequency. See, the maximum usable frequency, according to the definition, it is defined as the maximum frequency at which a wave is returned to the Earth for a given distance of propagation. For a given distance of propagation here. So here the given distance means the distance is fixed here. If this is a transmitting antenna and if this is the receiving antenna, this is the transmitter and this is the receiver. So this is the surface of the Earth here. So we are going to transmit a signal with 5 MHz here. With the 5 MHz, it goes to the ionospheric region and it comes return to the Earth here. So again we are going to change the frequency with the 10 MHz of frequency. It is going and coming back to the Earth. Again, if we increase the frequency to 15 MHz, so here the signal is going to the ionospheric region, it is going back to the receiving point here. So here this 15 MHz is assumed as maximum usable frequency. So this is known as the maximum usable frequency. And similarly, what is the critical frequency? So here critical frequency. So we need to determine the critical frequency. Here the highest frequency at which the wave is reflected from the ionospheric region at vertical incidence, we call it as critical frequency. Suppose here there is a transmitting antenna on the curved surface of the Earth. We are going to locate this antenna in this direction like this. And here there is a surface of the Earth. And we are sending the signal vertically. So vertically means this is vertical. So let us assume here the antenna direction. Suppose the antenna direction is like this. And here the antenna is located like this. And we are going to send the signal vertically here. We are going to send the signal vertically. So here the signal comes back to the Earth here. So here there is a receiving antenna. This is the receiver. This is the transmitter. So here the highest frequency at which a wave is returned to the Earth at vertical incidence, we call it as the critical frequency. So at what frequency we need to transmit for a wave to return to the Earth, we call it as the critical frequency, which is denoted by the symbol Fc, and FMUF is nothing but the maximum usable frequency. The maximum usable frequency. Now, as per the data given, d is the distance of propagation. So d is nothing but the distance of propagation between the two stations. So between the two stations, it is given as it is 1500 kilometers, and also the height of ionospheric region h represents the height of the ionospheric region here. It is given as 250 kilometers. Ionospheric region is given as 250 kilometers. The maximum usable frequency, f MUF, it is given as 37.95 megahertz. 37.95 megahertz. Now here the earth is assumed as flat here. The earth is assumed as flat. And what is the critical frequency? So what is the critical frequency? That is Fc is equal to, we need to find out. So based upon this data, we are having a relationship between the f MUF and Fc. So we are having a relationship between the critical frequency and the maximum usable frequency. So which is given by f MUF is equal to Fc into root of d by 2h whole square plus 1 here. So what is the f MUF given here? 37.95 megahertz. So 37.95 into 10 power 6. This is equal to Fc into square root of, what is the value of d here? D is given as 1500 kilometers into divided by 2 into h is given as 2 into 250 whole square plus 1 here. So this we can further simplify as Fc square root of, so here we can get here 0 0 get cancel, and this is 6 and 2 ones 2 3s here. So you will get 3 square plus 1 here. So this is equal to, you will get Fc into root 10 here. Fc into root 10 here. So from this equation, we get the value of Fc, the critical frequency is given as 37.95 into 10 power 6 whole divided by root 10 here. So what is the value of root 10 here? The root 10 is nothing but it is 3.3. So 37.95 into 10 power 6 whole divided by, this is 3.3. So root 10 is, if you further simplify this, the mathematical expression, this is approximately equal to 12 megahertz. So you will get approximately 11 point something. So this is approximately equal to 12 into 10 power 6 hertz here. So 12 into 10 power 6, this is approximately equal to 12 megahertz here. So why? Because mega means 10 power 6 here. So the critical frequency for a given maximum usable frequency, so we got it as 12 megahertz. So we got it as 12 megahertz. So here we have derived, all the data will be given in the problem here. So we need to know only the formula, that is the relationship between the maximum usable frequency and the critical frequency, that is f MUF is equal to Fc into root of d by 2h whole square plus 1. So this is the equation for flat earth. This is the equation for flat earth here. So you can see in the problem here, the d, the distance of propagation 1500, h is equal to 250 kilometers given data, and MUF is equal to 37.95 megahertz. And for this data, we have calculated the f MUF value, Fc into root of d by 2h whole square plus 1. And this is, we substitute the values of d, h and MUF and simplify the mathematical calculations. We will get Fc is equal to approximately 12 megahertz. So this is critical frequency. This is critical frequency. Now let us do the second problem here. It is required to establish a shortwave communication between 2 points on Earth's surface separated by 1200 kilometers. Calculate the MUF, maximum usable frequency, and angle of takeoff of the transmitted wave from the following data. The highest signal frequency returned to the Earth after vertically upward direction propagation is 7.2 MHz, and the virtual height of the ionosphere layer it is 200 kilometers. Assume the surface of the Earth to be flat. So assume the surface of the Earth to be flat. So similarly as how we have did the previous problem, similarly we are going to simplify this problem also. And here we need to calculate the MUF value and the angle of takeoff. We need to calculate two things. One is the maximum usable frequency and the angle of takeoff. How much angle we should propagate at what angle we should propagate the signal so that it will be returned vertically downwards. So here, according to the given data here, we can see here the distance between to establish a communication, the distance between the two stations, it is given as D is equal to 1200 kilometers. D is equal to 1200 kilometers, out of which we can write as 1200 into 10 power 3 we can write here. And similarly, the highest frequency which is vertically returned to the Earth, when we transmit the signal vertically upward, the wave is going to return to the Earth. We call it as a critical frequency. So according to the definition of critical frequency, the highest frequency at which a wave is returned to the Earth at vertical incidence, we call it as a critical frequency. Here the highest frequency it is given as 7.2 MHz. So what is the 7.2? The 7.2 is nothing but the critical frequency. It is 7.2 megahertz. And H, the height of the ionospheric region is 200 kilometers. So we need to define all the alphabets which we have defined like this. D is equal to, D represents what? The distance. D represents the distance between the 2 points on Earth. The distance between 2 points on Earth is given as 1200 kilometers. So this we can simplify as 1200 into 10 power 3. And similarly, FC, the highest frequency. The highest frequency it is given as 7.2 megahertz. 7.2 megahertz is we write as 7.2 into 10 power 6 hertz here. And similarly, we can write H. H represents what? It is the height of the ionospheric region. It is the height of the ionospheric layer. It is given as 200 kilometers. So what is 200 kilometers? It is, we can write as 200 into 10 power 3 here. Now from this data, we need to find out the value of F MUF. We need to find out the value of F MUF here. So here we are going to again use the same equation. There is a relationship between the MUF, that is the maximum usable frequency, and the critical frequency. It is given by F MUF is equal to Fc into root of D by 2H whole square plus 1. So this is equal to, what is the critical frequency here? The critical frequency is given as 7.2 into 10 power 6 here into root of D. The distance is given as 1200 by 2 into, what is the value of height here? 2 into 200 plus 1. This is whole square here. So if we simplify this, you will get 200 ones and 206 here, 2 ones and 2 threes, and 3 square means 9 here. So 7.2 into 10 power 6 into root of 3 square means 9, 9 plus 1 here. So this is equal to 7.2 into 10 power 6 into root 10 here. So here root 10 means you will get approximately 3.3 something like that. So 7.2 into 10 power 6 into 3.33. So approximately you will get 22.7 into 10 power 6 hertz. So this is approximately equal to round off to 22.7 megahertz here. So this is the maximum usable frequency. Maximum usable frequency, that is F MUF here. Now another parameter we need to find out here, the angle of takeoff here. So what is the angle of takeoff here? Or what angle we need to transmit the signal here? Now let us indicate by means of a diagram here. So here this is the h value. Let us assume this as the beta, the angle of takeoff as beta, and this is the angle of incidence. This is the angle of reflection. Assume this the total distance as the d here. This becomes a d by 2 here. Assume this as O, this is A and this is B here. Assume this as AB. A is the transmitting antenna, B is the receiving antenna. The height h represents from the surface of the earth, and d is the distance between the 2 points on the earth, that is between A and B here. And from the figure we can write tan beta. Tan beta is equal to opposite side to theta by adjacent side to theta. So here OAB, suppose let us assume this as C. This is nothing but h means opposite side to theta. This is OC divided by AC. So what is OC here? It is h by AC d by 2. So from this equation we can find out 2h by d here. So here from this equation we can find out the value of beta here. So beta is equal to tan inverse of 2h by d here. So tan inverse of 2 into, what is the value of h given in the problem? It is 200. 200 into 10 power 3 whole divided by the distance is 1200. 1200 into 10 power 3 here. So 10 power 3, 10 power 3 get cancelled here. And this is 200, 206. This is equal to tan inverse of 1 by 6 you will get. So this equal to, we'll get 18.4 here. So we'll get 18.4. So this is the value of takeoff. The takeoff is nothing but it is 18.4 degrees. So at the angle of 18.4 degrees, we need to transmit the signal so that the wave is returned to the earth at a height from a height of 200 kilometers. So this is the problem 2. The given data, 1200 distance, FC is 7.2, and the height of the region is 200 into 10 power 3. And from this we are going to substitute all this data, this and this data in this problem here, and we are getting the equation as 22.7 into 10 power 6 hertz here. So this is the angle of takeoff d and d by 2 here. So we are going to calculate 2h by d. H is given as 200 and d is given as 1200 here. If you simplify, you will get 18.43 degrees. We will come to the last problem, that is a transmitting antenna mounted at a height of 120 meters radiates 15 kilowatts of power equally in all directions at a frequency of 50 MHz. Calculate the maximum LOS range field strength at receiving antenna mounted at a height of 16 meters at a distance of 12 kilometers. So we need to calculate the maximum LOS range. That is DLOS. It is given by 4.12 into root HT plus root HR. So as per the given data, the heights are given as HT is given as 120 meters and HR it is given as 16 meters. Now we need to establish a direct path communication between the transmitting antenna and receiving antenna. So what must be the minimum distance? So at what distance we need to maintain for these heights of the transmitting antennas so that a direct path can be established between the two antennas. So this we call it as range in space wave propagation. We can also simply call it as LOS communication. So as per the formula, we can calculate root HT. It is 120 plus root 16 here. So 4.12 into root HT plus root HR is equal to, you will get 61.61 in kilometers. So DLOS is equal to 4.12 into root HT plus root HR. If we simplify, you will get 120 root 120 plus root 16. It is equal to 61.61 kilometers. And the second problem, that is a field strength. So what is the field strength at the receiving point? So we are having a formula to find out the field strength in space wave propagation. 88 root P HT HR by lambda d square. So here, what is the frequency given in the problem here? The frequency is given as 50 megahertz. So from this 50 megahertz, we need to calculate lambda. Lambda is equal to C by F. C is equal to 3 into 10 power 8. The frequency is 50 into 10 power 6. So if you simplify this, you'll get the lambda as 6 meters. The lambda as 6 meters here. Now let us substitute the data. 88 into root P. So P is given as 15 kilowatts here. P is given as 15 kilowatts. So 15 kilowatts it is given. Kilo means 1000. So 15,000 into HD means 120 into it is the height of the receiving antenna is given as 16 whole divided by lambda. The distance of propagation is 12,000 whole square. 12,000 whole square here. So the formula to determine the electric field strength the receiver is given by 88 root P HD HR by lambda d square. As per the given data, the amount of power is given as transmitted is given as 15,000. The height is given as 120 into 16, transmitting antenna, receiving antenna, and the frequency is 50 megahertz, where we calculated the value of lambda as 6 meters, and D, the distance between the 2 points A and B from the transmitting antenna to the receiving antenna is given as 12,000 meters. So we have substitute the data and simplify, you will get 23.95 millivolts. You will get 23.95 millivolts here. So this is how to find out the value. So D max equal to root HD plus root HR. Substitute the value of HD and HR, you will get 61.61 kilometers. And similarly, find out the value of ER is equal to 88 root P HR by lambda d square. Substitute the data here, given data of the problem. And if you simplify the mathematical analysis, you will get 23.95 millivolts. Calculate the attenuation at a frequency of 600 megahertz when the distance between the transmitting and the receiving antenna is 40 kilometers and gains are 20 dB. So how much the wave is attenuated between the transmitting antenna and the receiving antenna? So we need to calculate it. So here the transmitting and receiving antennas is separated by 40 kilometers. So the distance is given as 40 kilometers and the frequency is given as 600 megahertz. And the transmitting gain and the receiving gain are equal. It is given as GT is equal to GR is equal to 20 dB. Assume GT and GR as transmitting antenna gain and receiving antenna gain, and frequency is 600 megahertz, and the distance between the two stations is 40 kilometers. So we are having a path loss formula to determine how much amount of spatial path loss, LS. So LS indicates the spatial path loss is given by 32.45 plus 20 log F plus 20 log D base 10. So this we substitute 32.45 plus 20 log 600 plus 20 log 40 base 10. So if you simplify this, you will get 120.056 dB here. So you will get 20.056 dB here. So this is the spatial path loss. And now we are having a formula. What is our total amount of attenuation? PR by PT is equal to GT plus GR minus LS. So GT is given as 20, GR is given as 20, and LS just now we have calculated, it is 120.056. It is 120.056. So if we simplify, you will get minus 80.056 dB here. So this negative sign indicates there is a decay of attenuation of the signal by 80 dB between the two stations. So between the two stations, there is the signal is going to attenuate by a value of 80 dB. By a value of 80 dB. So here we are having two formulas to determine the first LS. So LS means the spatial path loss given by 32.45 plus 20 log F plus 20 log D kilometers, and we are having an equation representing the powers between the power ratio between the transmitting antenna and receiving antenna. So PT by PR is given by, this is PR by PT. Power received to the power transmitted is given by GT plus GR minus LS. So GT and GR represents the gains of transmitting antenna and receiving antenna. So as per the given data, we are having 20 plus 20 minus 120.056. If you substitute and simplify, you will get minus 80.056 dB. So this is the problem. Calculate the attenuation at a frequency of 600 megahertz. So GT is equal to GR is given 20 dB and D is equal to 40 kilometers is given here. We need to calculate the value of LS 32.45 plus 20 log D plus 20 log F, and LS in dB is equal to, if you simplify, you will get 120. So the ratios of power received to the power transmitted is given by GT plus GR minus LS. Substitute these three values here. If you do the mathematical equation simplification, you will get minus 80.056 dB here. So find the skip distance when the angle of incidence is 200 and virtual height is 50 kilometers. So given the angle of incidence here, the virtual height is 50 kilometers given. We need to calculate the value of skip distance. So we know that d skip is equal to 2h into root of f mof by fc whole square minus 1, and but f mof is equal to secant pi I into fc. So we can substitute this f mof value in the numerator here. So if you substitute this in the numerator, you will get secant pi I fc by fc whole square. Here fc get cancelled. You will get 2h. So if you simplify this, you will get 2h. D is equal to 2h into root of secant pi I whole square minus 1 here. Secant pi I whole square minus 1 here. So here we need to simplify. The angle of incidence given as 20 here. Substitute secant 20 whole square minus 1, and you will get 36.33 kilometers. So d skip is equal to 2h into root of secant pi I. So here what we should do is the value of f mof and secant. This is a secant law. So f mof is equal to fc secant pi I. This is secant law. So we need to substitute this f mof value in the d skip equation. So if you simplify it, you will get 2h into root of secant pi I whole square. The pi I is given as 20 here. Substitute 20. Secant 20 whole square minus 1 is equal to 36.33 kilometers we get. So this is the d skip value. So for references for these problems, you can verify antennas and wave propagation by U.A. Bakshi. Also, you can verify K.D. Prasad antennas and wave propagation, first edition 2001. So for more problems, you can also verify John D. Cross and also Balanis. So for more problems on these topics, path laws and field strength, you can verify John D. Cross, and another one is the Balanis textbook. So with this, we close the session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.